Ever wondered what it would sound like if two colossal black holes were to crash into each other billions of light years away? Well, hold on to your seats, because today we're exploring how scientists managed to listen to an event so big, it literally shook the fabric of space-time itself. Welcome to our channel. We're unraveling the story of gravitational waves, Einstein's brilliant prediction from over a century ago, and how two incredible machines, LIGO and Virgo, teamed up to hear the universe's biggest collisions. Stick around, because this is no ordinary bedtime story. It's the dawn of a new age of astronomy. Let's roll. Our tale begins in 1915 with a guy you've definitely heard of, Albert Einstein. He introduced something called general relativity, which basically redefined gravity. Instead of some mysterious force pulling you down, Einstein said gravity emerges from how mass and energy warp space-time, like a bowling ball on a stretchy trampoline. In Einstein's universe, if two massive objects like black holes or neutron stars collide, they create ripples or waves in that stretchy cosmic fabric. These ripples spread out across the universe at the speed of light, carrying information about their violent origins. He called them gravitational waves. Sounds epic, right? Here's the catch. Einstein himself thought they might be impossible to measure. They're incredibly tiny by the time they reach Earth. We're talking changes in distance 1,000 times smaller than the diameter of a proton. Who would even attempt to measure something so absurdly small? Enter the Laser Interferometer, Gravitational Wave Observatory, or LIGO for short, and its European partner, Virgo. Picture these as giant, ultra-precise rulers that can detect those minuscule wrinkles in space-time. LIGO has two main observatories in the United States, one in Hanford, Washington, and another in Livingston, Louisiana, while Virgo stands proudly in Italy. Here's the gist. A powerful laser beam is split into two perpendicular arms, each about 4 kilometers long. That's about 2.5 miles. The laser bounces back and forth between mirrors at the ends of these arms, and then the two beams are brought back together. Normally, the beams cancel each other out if the arms are exactly the same length. But if a gravitational wave passes by, it slightly changes one arm's length compared to the other. That teeny difference shows up in the combined light, telling us a wave has arrived. You might be thinking, wait, how do we measure something so small that it's 1,000 times smaller than a proton? Well, that's the jaw-dropping precision of LIGO and Virgo. They measure changes on the scale of 10 to the negative 21st power meters. That's like measuring the distance from here to Alpha Centauri, over 4 light years away, to within a hair's breadth of accuracy. September 14th, 2015. While we humans were going about our daily routines, commuting, sipping coffee, hitting snooze, LIGO had just been upgraded to its advanced LIGO configuration. Then, around 5 a.m. Eastern Time, a signal was captured. At first, the scientists didn't believe it. Could it be just noise, an artifact? But soon it became clear. This chirp was the real deal. Two black holes, each about 30 times the mass of our Sun, had merged 1.3 billion light-years away. Let that sink in. This collision happened before multicellular life even formed on Earth, but the gravitational waves only arrived to us in 2015. Mind-blowing, right? That faint whoop changed everything. On February 11th, 2016, the LIGO team went public with the announcement. The scientific community erupted. This wasn't just big news, it was Nobel Prize-worthy stuff, and indeed, the 2017 Nobel Prize in Physics went to 3 of LIGO's key founders. And just like that, Einstein's 100-year-old prediction leapt out of the textbook and roared into reality. LIGO wasn't fighting this battle alone. Across the Atlantic, Virgo was refining its own laser interferometer. In August 2017, Virgo joined the gravitational wave detection game, And guess what? Just 2 weeks after Virgo switched on, a new gravitational wave signal popped up. This time, the wave pattern told us a pair of black holes about 1.8 billion light-years away were merging. With a 3-detector network, both LIGO sites and Virgo, scientists pinpointed the source's location in the sky with much greater accuracy. Then came the showstopper. On August 17th, 2017, another signal arrived. But this one looked different, way different. Turned out, it was the first gravitational wave detection of 2 neutron stars colliding. Neutron stars are basically stellar corpses, so dense that a teaspoon of their material weighs 1 billion tons. When they merge, they create a spectacular explosion called a kilonova, forging heavy elements like gold and platinum. For the first time in history, we observed the same event in gravitational waves and in traditional light-based telescopes. This multi-messenger astronomy allowed us to piece together a cosmic puzzle in unprecedented detail. We learned how elements heavier than iron form, and even narrowed down the speed at which the universe is expanding. The detection of gravitational waves isn't just about proving Einstein right, though that is super cool. It marks the start of a new era in astronomy. We're no longer limited to just looking at the universe through telescopes. Now we can listen to it. These waves tell us about phenomena that don't emit light, like black hole collisions, which is something we could never see with electromagnetic-based observatories. Think of it this way. For centuries, we've only had eyes on the cosmos. Now we have ears too. Imagine being at a rock concert but not hearing the music, only seeing the lights. That was astronomy before gravitational waves. Now we have both the lights and the sound. That's synergy right there. So how do LIGO and Virgo achieve these mind-boggling measurements? It's a perfect marriage of precision engineering and cutting-edge physics. Vacuum tubes. Each arm is kept under extreme vacuum conditions so air molecules don't mess with the laser beam. Mirrors. They're made of ultra-pure glass and polished so finely that any imperfections are smaller than a fraction of a wavelength of light. Seismic isolation. Tiny earthquakes, passing trucks, or even ocean tides can shake the mirrors. So the system uses advanced suspensions, making the mirrors float to minimize vibration noise. Lasers. Extremely stable, high-power lasers ensure the light doesn't fluctuate significantly. Every tiny detail matters. Even someone sneezing near the apparatus could, in theory, register as noise if not properly isolated. It's pure engineering genius on the brink of science fiction. What's next? Well, LIGO and Virgo have more friends joining the party. Kagra in Japan is an underground gravitational wave detector that began operation recently. LIGO India is on the horizon, further expanding the network. The more detectors we have, the better we can triangulate signals, and the more we'll learn about these cosmic cataclysms. We're also eyeing space-based observatories like LISA, Laser Interferometer Space Antenna, to detect lower frequency gravitational waves, like those from supermassive black holes millions of times heavier than the Sun. If LIGO is a microscope for black hole collisions, LISA will be a wide-angle telescope for the biggest monsters in the universe. Since 2015, LIGO and Virgo have recorded dozens of black hole mergers, a handful of neutron star collisions, and keep adding new events to the list. Each detection helps refine our models of stellar evolution, black hole populations, and even the expansion of the universe. We're painting a richer picture of the cosmos, one wave at a time. Now, if you're as mesmerized as I am by gravitational waves, go ahead and hit that thumbs up. Tell me in the comments, which cosmic event do you think we'll detect next? Another black hole merger, a neutron star collision, or something even more extraordinary? I can't wait to hear your theories and predictions. And speaking of cosmic possibilities, don't forget to subscribe and ring that bell icon. That way, you'll never miss our next deep dive into cutting-edge science, from quantum computing to the latest exoplanet discoveries. Let's keep exploring the universe together.